see those slides? Great. So I just want to thank the organizers for inviting me to speak at this exciting seminar series. I see some familiar names and I see a lot of unfamiliar names, so I'm looking forward to presenting and then getting to answer any questions that anybody has at the end of the talk. So as mentioned, today I'm going to be talking about the temporal dynamics of the spectral sensitivity of human circadian phase resetting and melatonin suppression. I am currently an assistant professor at Merrimack College. I recently moved there. I had previously been at Brigham and Women's Hospital and Harvard Medical School for the past about 20 years. I'm still part-time at Harvard Medical School as well. And most of the work that I'll be talking about today will be based on work that was done at Brigham and Women's and Harvard Medical School. So just to outline my talk for today, before I get into the main focus of the talk, which is going to be on the temporal dynamics of the spectral sensitivity to light in humans, I did want to take a couple of minutes to just review some of the key properties of light. Not knowing exactly who is in the audience, I think it's important to kind of look at the history of where we've come from in terms of what we understand about the properties of light in humans, how it relates to the mammalian system more broadly. And then also kind of take this opportunity to talk about some of where I think there are current knowledge gaps and where I think there need to be some future directions and future experiments. So the properties that I'll be quickly reviewing today, and like I said, I'll be focusing mostly on the properties of the duration of light exposure as well as the spectral composition. But I don't want to leave out the importance of the intensity, or what we more generally refer to as the irradiance of the light exposure, the timing of light exposure, which is very critical for a lot of the responses that we see, and then also talking a little bit about the, for lack of a better phrase, what I'm going to call the pattern of light exposure. So this includes intermittent light exposures, as well as the overall photic history that somebody has been exposed to. And so just to start, I'll start very simply by just reviewing some of the literature in terms of intensity, or again, what we more refer to as irradiance these days, especially when we're talking about spectral, different wavelengths of light. And just to highlight that in 2000, Jamie Zeitzer and colleagues constructed these beautiful intensity response curves, which have been very instrumental to a lot of the work that I've done over the years, looking at both the response of the system to intensity of light for phase resetting, as well as melatonin suppression. And just for context, these were exposures that were all done in the early biological evening. These were 6.5-hour light exposures. At the time, it was thought that humans needed to have very long light exposures in order to elicit a strong response. As I'm going to tell you later in this talk, that isn't necessarily the case, as we now know. But really, the importance of this work was really highlighting the fact that the circadian system, both for phase resetting and for melatonin suppression, was really sensitive to a lot lower light intensity than I think we had expected, at least in humans. Now, rodent work and other mammalian work had already discovered that the system was sensitive to lower light levels, but it really wasn't considered in humans until some of this work looking at these intensity response curves were done. And just to highlight, I'm showing here the values for the ED50, the effective dose, so what it takes to get 50% of the response. And for both melatonin phase resetting as well as melatonin suppression, you can see that it's around 100, what we back then called 100 lux. This is not melanopic lux, this is just polychromatic lux. So something else that we now, I think, know and take for granted is that the timing of this light exposure is very important. So if I can just get my cursor so that I can point to things. The light exposures that I showed on the previous slide were all done sort of in this part of what we call the phase response curve. So in the early biological evening, right around the time of dim light melatonin onset, we got strong phase delays in that region. But what the phase response curve tells us is that if we shift the timing of that light exposure to more towards the late biological night, which would be early morning hours, we get strong phase advances of the system. And we can also see that although there may be a slight dead zone in the phase response curve, basically at light exposure at any time of day elicits some sort of phase resetting response. And so as we keep in mind some of the studies that I'm going to talk about today, most of them were done in the early biological evening to really maximize the phase delay that we observe. But keeping in mind that these properties may likely be also true at other parts of the phase response curve as well. So something that I am going to spend a lot of time talking about today is the impact of the duration of light exposure. And some work that was done just a little over a decade ago in humans really took the opportunity to expand on what was done early on, which was to look at these kind of 6.5 hour light exposures where we got about 3 hours of phase delay, and look at what happens when we do shorter and shorter light exposures. So Anne-Marie Chang and colleagues constructed what we call a duration response curve. We're looking at as short a light exposure as 12 minutes, just over one night, all the way up to 6.5 hours. So these other increments are, actually can't remember what this one is right now. It's less than an hour. I think it's maybe 30 minutes, 1 hour, 2.5 hours, and 4 hours. And we see that there's this obvious progression where the longer the light exposure, the more phase delay that we see. We actually expanded that work based on some modeling that we had done with Professor Richard Cronauer at Harvard University, because he suspected that actually the system was even more sensitive. So we were already really surprised that 12 minutes elicited, a fairly strong response on the order of about a half hour of phase delay. And so when we expanded those studies out to doing shorter light exposures, so 15 seconds and 2 minutes, we found that even those really short exposures elicited very strong phase resetting of about 60 minutes. And this again is in the delay region of the phase response curve, where we expect to see kind of maximum phase delay setting. Something else that we also started looking at was the start looking at combinations of different properties. So if we look at the duration relative to timing, we can construct phase response curves that use different durations of exposure. So this is just one example of a set of phase response curves that I published in 2012. And in these phase response curves, we have a 1 hour phase response curve versus a 6.7 hour phase response curve. And again, what you can see matches what we see in the duration response curve, that we do get a smaller phase shift with 1 hour versus 6.7 hours. But we still do see a phase response across time. And so we still do see, I think actually now the axis the axis is still the same as the others. So we still see phase delays relative to kind of timing around DILMO, and then phase advances, later in that biological night. The magnitude of them are just smaller when we have shorter light exposures. So I want to take a second to sort of talk about the duration response curve that we observe in relation to what we see across different mammalian species. And so in 2019, this was actually work that I worked on with Professor Richard Cronauer for over a decade as we sort of pieced together all of this information and put together all of these studies that we needed to construct these duration response curves. But this is just the same data on the previous slide, just replotted in a different way. So basically we have our 15-second, our 2-minute, and our 12-minute data. And then we have our longer light exposures from the original Chang study plotted up here in the circles. And basically what we're just showing is that if you compare the phase resetting by duration in humans to the phase resetting in mouse. And so we took these data from a couple of papers that had been published in the early 2000s from groups in Europe. What you see is sort of this remarkable consistency, almost as if the system has been conserved across species. And something that I'd like to highlight, and I'll come back to this in a little bit, is that there seems to kind of be this inflection point where initially, and it'll be easier to see this on a plot that I show later, initially what you have is this kind of very fast response for every kind of additional second or minute of light exposure that you have. You get a really strong phase resetting response. And that eventually starts to slow down where any additional time added on to the light exposure does still progress the phase resetting, but it does so at a reduced rate or yield compared to the shorter duration light exposures. And if you look across species, you can see that not only is that very well conserved across across the durations, but that where we think the inflection point might be, where we think that the system might be transitioning from what we've called this fast response to this slower, more sustained response, actually ends up being right around in the same spot. And that's at a duration, I have it here in log seconds, but in terms of minutes, it's at about 36 to 37 minutes. And that's going to be really important when we start talking about the duration by spectral composition interaction that I hope to show you in a little bit. So that's just something to keep in mind for now. But getting back to some of the key properties, I think kind of the newest property that we've introduced into our lexicon, so to speak, is what happens with different spectral distributions of light. So again, a lot of my examples focus on work that was done at Brigham and Women's because that is the group that I was working with. But in 2003, Steve Lockley and colleagues showed that if you have monochromatic light exposures at 460 nanometers, which was meant to sort of trigger the melanopsin system, which had just been discovered, just a few years prior, versus a light exposure at with a monochromatic 555 nanometer wavelength, which was at the time, that's the peak of the 3-cone visual photopic system. So that's why that particular value was chosen. Basically, you see that, again, the phase shifting is much stronger in response to the blue light meant to trigger the melanopsin system versus the what appears to be green light that is thought not to trigger that system. And the same is true of melatonin suppression. So if you expose individuals to those two wavelengths of light, you see very strong melatonin suppression in response to the shorter wavelength light. You do initially see in some individuals some suppression from the green longer wavelength light, but what you really see is that suppression does not stay suppressed for very long. And so there's potentially this prompt response, and again, we'll talk about kind of why, other evidence for why that happens in a few minutes. So you initially see a prompt suppression, but then the system sort of rebounds and melatonin continues to be produced. Whereas in the blue light, you really don't see that, except potentially in this one participant. We've also looked at spectral by timing interactions. So we have constructed a PRC to 480 nanometers of light. So that is the darker solid black line in this figure compared to our original 6.7 hour polychromatic light exposure. And you can see that the magnitude of responses is very similar, suggesting that 480 nanometers, which again is triggering the melanopsin system, at least that's what we presume is happening, is enough, and that really all of what we see in the white light exposure is probably coming from that part of the system. We've also looked at spectral by intensity interactions. So we have originally constructed irradiance response curves just for the 460 versus 555. Pretty soon, I am going to show a more complete picture where we've done this across an entire action spectrum. But just to highlight this early work, because it really did drive a lot of the later work. What was interesting about these irradiance response curves, rather, is that the phase resetting magnitude basically changed relative to the irradiance. So actually, at lower irradiances, we actually got a stronger phase resetting response from the longer wavelength light. And it was only at higher irradiances that we saw that the shorter wavelength light, the 460 nanometer stimulus, actually produced a stronger response. And again, just to orient you, because you're going to see this again, these values here in the dotted lines are showing the ED50 value, but they're showing basically the log photons needed to elicit that ED50. And so you can see that generally speaking, it takes a lot more photons of the longer wavelength light to elicit the same magnitude of phase resetting response as from the shorter wavelength light. And that's just something, again, to keep in mind as we progress through the rest of the talk. I would be remiss not to talk a little bit about the pattern and the photic history, because I do think it is really critical and something that I think gets a little bit ignored in a lot of these experimental studies. So we know from a study by Chang and al., as well as many other studies, that there is an effective prior light history. And so what this is basically showing is that if somebody had been in an intensity of 90 lux prior to a light exposure to elicit either melatonin suppression or phase delay, that they would actually have a much lower effect of that subsequent light exposure than if they were in a dimmer light condition prior to going into that light exposure. And that's actually very consistent with the physiology. We do know that when someone is dark adapted or dim light adapted, in this case, they tend to have a very stronger response. And we'll talk a little bit about the physiology behind that. And I also want to mention, because I think that these data are very interesting, and I'm just still trying to wrap my head around them. We're trying to reconcile how these data fit in with what we've modeled of the circadian system. Of course, I'm talking about Dr. Zeitzer and colleagues and his temporal integration of intermittent light flashes. And so looking at light flashes that are just a millisecond long, but having a train of them over an hour with different interstimulus intervals. And we see very strong phase resetting, which actually at the moment, as far as I know, we can't explain those by any of our current mathematical modeling approaches. So that's certainly an area, I think, for future research. But today I do want to focus on the interaction between the duration response curve and the spectral sensitivity. And I want to return to this figure that I showed from the review that I did with Richard Cronauer and colleagues back in 2019. And I'm just showing a slightly different version of it, where we've plotted on the x-axis light exposure duration in minutes, So you can really see what the different light exposures are. And this figure really highlights just how rapid the response is over the first 12 minutes of light exposure. So we go from having about a half hour of phase resetting in response to just 15 seconds of light to over an hour with 12 minutes of light. And then, as I mentioned previously, then we see a bit of a slowing down in the, if you think of it as the rate of return on that investment in that additional light exposure. So we do still see that the phase resetting increases as duration increases, but it does so at a much lower rate. And the inset of this figure is just basically showing that on a different scale. So we initially get a very rapid yield of phase resetting from each second or minute of light exposure. And then eventually we get a very small but sustained incremental response across the remainder of that light exposure. And as I mentioned, that inflection point we calculated to be somewhere around 37 minutes, and that's very consistent across mammalian species. Now, the way we think about this was published in 2019, but really Cronauer had already been thinking about the properties of the system all the way back in 1999 and even earlier when he did his original models in 1990. And the way he modeled light really does match what we understand about the physiology today. And he actually based this on the response of the cone and the cone photoreceptors. And now we know more about the IPRGCs and the melanopsin response, and it does seem to match. And I'll just highlight here that this is just showing what happens when there is a light exposure. So initially they're in dark, we turn the light on, and I'll just direct you to figure panel C, which basically is showing the response of the light drive onto the circadian pacemaker. And so initially what Cronauer modeled was this very prompt response over the first few minutes of light exposure, as we now see experimentally in the duration response curve, followed by this more sustained response. Now, the only difference between the panel on the left and the panel on the right is that we just didn't make the strength of this prompt response as large as it actually is. And so that 1999 model could not actually predict that we would get a 40 to 50 minute phase delay from a 2-minute light exposure. It really, but the physiology is there, the mechanism is there. It's really just the gain parameter that we would need to change in order to get that magnitude. And so this was already in place. We now also know from various works, and I'm just using Dave Berson's study as an example, that this is actually how the cones and the IPRGC or melanopsin respond, is that we see a very fast or prompt response from the cones. Basically, as soon as the light is turned on, they start firing. And the IPRGCs and melanopsin in particular do fire, but they take a little bit longer. So they're not firing as soon as the light exposure starts. They're, lagging a little bit, they're sluggish. But then that response is sustained. And so coming back again to this figure, what we proposed is that possibly that the short light exposures that we're seeing are primarily due to cone response, and that the longer light exposure, that sustained response, is really coming from the IPRGCs and specifically from melanopsin. So coming back to some of the work that we did just looking at 460 versus 555, we couldn't do this for phase resetting because for phase resetting, you really get one shot to measure it. You basically measure phase on one day, you give the light exposure on the next day, and then you measure phase again the following day. And so you can't really see that time course of what's happening during the phase resetting, but you can do that with melatonin suppression. And so what we did initially in this study was we looked at the melatonin suppression across 6.5 hours, but we calculated it out at different in this case, quartiles across that 6.5 hours. So we could look at what happened to suppression in the first quartile, then the second quartile, the third, and the fourth. And we can fit different irradiance response curves to each quartile to see what the suppression looks like across time. And so what we found in this study was that at the early part, so over the first about 90 minutes or so of that light exposure, we see that there's approximately equal suppression happening from both the short wavelength and the longer wavelength light. And this is pretty consistent with what we saw in those figures that, we initially saw a pretty prompt suppression at 5:55 that then eventually, returned back to baseline levels of melatonin. But early on in the light exposure, we see equal suppression. It's only in the later part of the light exposure, really going beyond about 90 minutes, that we see these two curves start to really separate, where 460, the shorter wavelength light, is much more effective at maintaining suppression than the longer wavelength light. And so this suggests that in the later part of that light exposure, the suppression and maybe also the phase resetting, although we don't know, is primarily short wavelength driven. And now the question really is that a cone response from the S cones, or is that a melanopsin response? And that's what we are going to answer next. So I want to bring our attention now to how we determine where the sensitivity of the system is in terms of wavelength. And so again, early on, these two action spectra for melatonin suppression were published within just a few weeks of each other. The one on the left is in response to a 30-minute light exposure. The one on the right is from a 90-minute light exposure. And what I want to draw your attention to mostly is that the peak of this action spectra, showing that the peak melatonin suppression occurs at what we call a lambda max, at a wavelength of about 460 nanometers. So very similar to what we did in our later studies looking at phase resetting. So that was partly why 460 was chosen as that short wavelength exposure. And one thing that I do want you to notice is that based on what I just showed, especially for the 30-minute, but also for the 90-minute exposure, if these irradiance response curves are accurate, we should actually see that 460 and 555 should be approximately equal in terms of suppression. And it turns out that that's not actually what we see in these original action spectra, and I'll try to explain why that is. So 460 would be about here, 555 is down here, and you can see that there's a significant difference in the log relative sensitivity. So that doesn't really match what we see in these curves. Now, Timothy Brown, who I think spoke earlier in this seminar series, so I'll just try to review this really quickly, actually took these two action spectra and did two things with them. So additional data were added to both of them. So specifically data that both extended out to the shorter wavelengths and also, just to the shorter wavelengths. And something else that was done is that these irradiance response curves were refit so that they were basically what we call univariate. So the idea being that you fix the upper and lower bounds of those basically logistic curves so that everything is basically on the same scale. And so what you see happens is that the 460 and the 555 now become somewhat more aligned. There's not that dramatic difference between them. And what's interesting about what Timothy Brown did is that he took both of these action spectra and he fitted two curves to them. He fitted an opsin model that was melanopic only, so basically with a peak at about 480, which is where we know the peak sensitivity of melanopsin is. But he also fit a model that was a combination of both melanopic and S-cone. So that would be the line here in it's like a lightish purplish blue color. And here I think it's this dashed line. And so what this actually shows us is that the melanopsin plus S-cone model was a better fit to both of these action spectra compared to just a melanopic only system, which suggests that especially at these shorter light exposure durations, we have some contribution of the S-cone that is separate from the melanopsin system. And again, this is consistent so far with what we see from the modeling work. I'll just go back, where we think this prompt response is being driven by the cone. And now this is phase resetting, but the same we expect also to be true for melatonin suppression. And it's similar, maybe not completely the same as what we see here, but I'm going to show you some new data that suggests that there is some S-cone contribution. And so the one drawback of these two studies is that, yes, we now know, or we now have some idea of what's happening at the shorter durations, but we don't know what happens at longer light exposures. And so what we wanted to do is we wanted to basically extend the original study that we did, which focused again on just 460 and 555. So those were those original curves that I showed you. And we basically expanded that out to 6 wavelengths with the goal of constructing an action spectra like these two, but for a 6.5 hour light exposure so that we could really see how do things change, not just from 30 minutes to 90 minutes, but also over a longer duration exposure. And so just to talk about what we did in the study, this was a 9-day inpatient study. This is the same experimental setup as some of the earlier studies that I showed. We gave a 6.5 hour light exposure during the biological night, and this was all timed relative to the subject's habitual sleep-wake time. We looked at 6 wavelengths, so running from 420 all the way up to 620. We did a range of irradiances at each wavelength, so from very low irradiance to fairly high irradiance. All of these were done in a Ganzfeld dome, which you can see there, so it was all very targeted exposure. I will also say that we did this with pupils dilated, so we're getting maximum light into the system without the impact of any constriction for the brighter light levels. And we can talk about the implications of pros and cons of that for data interpretation. And so what we did was we constructed irradiance curves at each wavelength, and here they are for melatonin suppression. You can see plotted here the goodness of fits, but also you can see the ED50 values and the photon density at which those ED50 values occurred. What you're looking for in an action spectrum when you replot these is you're looking for the one that is the lowest, and actually that happens to be at 507, which is the peak of the rod opsin. That's why we picked 507 in particular. We can't really explain right now why that one ends up being the best fit and not 480 as we might have expected. You'll see that 480 in a lot of these plots is actually kind of suboptimal. But when we fit a single opsin to this action spectrum, we do get a lambda max or peak at 481, so right around that melanopsin peak. You'll notice that in the action spectrum, we don't have a data point for 620, and that's because we couldn't get a reasonable fit for that. We really got no measurable melatonin suppression response for the majority of participants up to a photon density of e to the 14th. I don't know if we would have gotten one if we had gone stronger, but we didn't include it here. So something that we did, similar to what Brown and colleagues did in their fits to the 30 and 90-minute light exposures, is we wanted to understand what are the contributions of the different cone and IPRGC/melanopsin systems to these responses. And so what we did is we took the absorbance spectra for each opsin, which I've plotted here. We also applied a correction for lens transmission. So all of our participants were relatively young. I think our age range was 18 to 35. We know that the lens yellows as individuals age, and that has an impact on the amount of blue light that gets into the system. So we did do a little bit of a correction, even though these are relatively young people, in order to account for that. And so the opsin curves corrected for lens transmission that we ended up with, we had one for S-cone, we had one for IPRGC or melanopsin response, and then we actually combined the L plus M cone based on some previous research. And partly because we only have 5 data points, and so we wanted to make sure that we had enough degrees of freedom to be able to compute these different fits. The equation that we actually fit is down here below, and we fit different channels of models. So we fit a one-channel system where we basically look just at the IPRGCs, meaning that these coefficients for the S cones and the L plus M cones were set to 0. We then did a 2-channel system where these were both IPRGC and S cone were active, but this term was at 0. And then we did one at all 3. And we actually did other combinations as well. We did without IPRGCs, looking at just SNL plus M cones. Those are all in the supplementary materials of the paper. But mostly I'm going to focus on the 3 channels that I just talked about. So if you look at the fit of the melatonin suppression data to a 1-channel opsin, so just looking at IPRGCs, so 100% contribution from IPRGC, we do get a reasonable fit. This is the mean absolute error that I'm reporting. A lower value is better. We also did root mean square error as a second goodness of fit measure. They're largely consistent with each other, so just in the interest of making sure the slides weren't too noisy, I just left those out of these figures, but you can find them in the paper. If we fit 2 channels, so IPRGCs plus S-cone, we see that the contributions, so the percentages are just reporting how much does that opsin contribute to the overall fit. We see that this is still IPRGC dominant. We do get a slightly improved mean absolute error. But it was actually the 3-channel system where we also added the L plus M cone and looked at, again, the mean absolute error went down, where we do see minor contributions from the S and L plus M cone, but again, across this entire 6.5-hour exposure, this is primarily IPRGC driven. So cross-sectionally, if we now take that and put that on the same scale, and I probably should have actually used the ones from Brown and colleagues rather than the original ones, but we basically do see that cross-sectionally, as time into light exposure increases, so as that duration increases, the peak sensitivity of melatonin suppression seems to be shifting more towards the melanopsin peak. Now, we can look at that not cross-sectionally across studies, but we can actually look at that within our own data. So again, breaking this down into these different quartiles of melatonin suppression, so looking over the first 97 minutes versus later into the exposure, we can fit these channels. And basically, this is a very noisy slide. I don't want to spend too much time on it in the interest of time. But what we found was that in general, the 3-channel system provided a better fit than the 2-channel system with just the IPRGCs and S cones. We really did need to add that L plus N cone opsin to get better mean absolute errors. And what you really see, kind of the take-home message here, is that early into the light exposure, in that first 90 or so minutes, there actually is very little contribution of the IPRGCs. Almost everything is coming from the cone system. And as it turns out, at least comparing the 2-channel with just S cone to the 3-channel that includes L plus M cone, that there seems to be about equal contribution from the shorter wavelength cones and the longer wavelength cones. But again, as we might expect based on everything we know about the physiology, as we move across time later in the light exposure, we see some of the contribution of those cone systems dropping off. And eventually, by the end of the light exposure, the major driver of the suppression is coming from the IPRGCs. Okay, so that's the message for melatonin suppression, that basically in the early part of the light exposure, which is consistent with what was found from the 30-minute exposure action spectra and the 90-minute action spectra, that there's some sort of cone-driven response. The difference between our work and the work of Brad and colleagues is that we do think that there's some L plus M cone contribution in addition to S cone. And then later in the exposure, it really is completely melanopsin, or almost completely melanopsin driven. Now, we can do something similar with the phase resetting. Unfortunately, we can't look over the quartiles because, like I mentioned, we can only measure phase shift at one point in time. But we did find some consistency in terms of that story. So here are the irradiance response curves for phase shifting. These were primarily phase delays because we gave the light in the early biological night. You'll notice that this time we do get a fit for 620. In this version of the action spectra that I'm showing, we didn't include 620 so that we could be consistent with melatonin suppression. But what I will say, in the paper that we published, we do include we actually include both with and without 620. The results are basically the same. So whether you have 620 there or not, we get the same, we come to the same conclusions. So the conclusion we come to here is that, again, as we might expect for a 6.5-hour exposure, this seems to be primarily melanopsin driven if we just fit a single opsin and allow it to pick where it thinks the peak is. Again, though, you'll notice that the 480 is actually not itself the most effective. We actually get better response from 460 and 507, and this is sort of just kind of regressing to the mean to fall at around 480. Again, if we look at our fits of our 1, 2 versus 3 channel options, here is where our results are consistent with previous findings, that there is a pretty significant S-cone contribution. Now, again, this is a phase reset over the entire 6.5 hours. We can't break it down into smaller durations unless we did completely different light exposures that were shorter and did irradiance curves for all of them, which would be very expensive. But what we can see is that just from these fits, it seems like S-cone is having a pretty significant contribution, such that the best fit peak from this 3-channel system is actually, 445, which is not very close to the melanopsin peak. So how do we sort of summarize that? What I would say is that for melatonin suppression, we think that this is driven approximately equally by the S and the combination of L plus M cones, whether that's primarily M or primarily L. We can't delineate from this because we just don't have enough degrees of freedom to do that. So certainly over the first quarter of light exposure, we think that's primarily a cone-driven response. And then after that, we think that that's probably a primarily melanopsin response. For phase resetting, the story is a little bit different. And here we think that the S-cones might be contributing very strongly for that reason that I talked about in the modeling work, is that prompt response over that first 12 to 30 minutes of light exposure may be coming from the cones because they just respond more promptly to light exposure. So that may be why we're seeing that the S cones contribute significantly to the overall phase resetting because of what's happening in the first few minutes of light exposure, and that may be coming from the S cones more so than the longer wavelength cones or the melanopsin system. Unfortunately, like I said, with phase resetting, it's really difficult. We can't say for sure this is what's happening unless we construct other action spectra. And so again, to do that, we would need to do another set of phase resetting experiments with a shorter duration of light exposure. Ideally, we would do something maybe at 30 minutes and then at 90 minutes to match what we already have for melatonin suppression. And so what we would expect we would find is that would still be S-cone driven, and probably even more so without having that sustained response from melanopsin. But as of right now, we don't have the experimental data to show that. Finally, I just want to leave us with some take-home messages. I hope that you've understood from both the historical background and also from this newer work that all of the properties are very important, and that the system is way more complicated than I think we ever expected. So really, when we're designing any sort of lighting intervention, we have to consider the duration of exposure that people are likely to have. You know, if it's an office setting versus getting up to go to the bathroom in the middle of the night, that's going to have a very different set of responses. We need to consider the spectral composition of course, but also the intensity, timing, and pattern and history of light exposure. And you know, one of the criticisms of a lot of the work, especially coming out of the Brigham and Women's Lab, is that a lot of our participants in a lot of our studies are dim light or dark adapted prior to the light exposure. So we're kind of seeing the you know, massive phase resetting and massive melatonin suppression, whereas if they weren't dark or dim light adapted, they may not have that same magnitude of response. And it's likely that in the real world, most people are not going to be dark or dim adapted, although you have to think about situations in which they would versus wouldn't be dim light adapted. So if you're waking up from sleep and exposing yourself to really bright light, that's different than if you're sitting in an office all day. With that said, I do think we need more experiments to examine these complex interactions across these properties. And again, I only really focused today on phase resetting and melatonin suppression, but there are obviously other non-image forming responses to light. So we don't have a lot of data on the alerting effects of light across all of these different interactions. We also don't have, although we do have more data emerging about the impact on subsequent sleep quality relative to these different properties of light. But clearly, we need more in order to really understand what's going on. So I just want to acknowledge some of my co-authors, particularly Maria Montedoter, who drove a lot of the spectral work. A lot of the modeling work was done, as I mentioned, by Professor Kronauer and colleagues. And then a lot of the studies that I showed, both the current study that I presented and previous studies, were done by many other colleagues across Brigham and Women's and across the world. So with that, I will open it up to any questions. I see a couple already.